So maybe this graph right is 10 dB. And from there you can find out what KP is. Any type 0 system will have this form to calculate it that way. Okay? So two things are, by looking at the low frequencies, you can identify the system type. That's good. Second thing, you can get the bonus is you can calculate KP. Because for a type 0 system, KP is non-zero, or is the only finite value. And you calculate it by equating this to 20 log KP and solving for it. Okay. So again, if you ever see a Bode diagram where the magnitude plot is horizontal, it must be type 0. It cannot be anything else. If you're okay with that, then we can go on to type 1 system. So type 1 system introduces you 1 over S. You have this system here, 1 over S, this is 1 over J omega. Because of this guy here, if you recall the Bode diagram, it's minus 20 dB per decade. So that means at low frequencies, you will always have this minus 20 dB per decade. So you see your Bode diagram with this. And remember the example that we did just now? Do you recall the sketching? At low frequencies, it has a magnitude of minus 20 dB per decade. So this time the system right is type 1. Do you agree? Because at low frequencies, it's this low. So the key point right now is once you know that it's true, you can also recover KV, not KP, KV stands for the static velocity error constant. Just now what we did was to find the intersection with the horizontal line. Now there is no horizontal line. Okay? So to recover this, there are two ways. You can decide to choose which way. One is you draw this line here all the way down and intersect with the 0 dB line. That frequency omega 1 will be equals to KV. Okay? This is KV. That's one way. The other way is you find out where is the omega equals to 1. You draw the line here and see where it intersects this original minus 20 dB line. And this value here will be 20 log KV. Okay, sum of KV. Both methods. Either you go all the way down to 0 dB, find this omega, and that's KV. Or find omega 1, go up to here and draw this and find 20 log KV and find the KV, you'll get the same value. So there are two ways for you to find KV from the Bode diagram of a type 1 system. Both are correct. So it's not like one multiplied by the other. So up to you. Okay? So I repeat one more time. So if you want to find the KV for a type 1 system, you find the low frequency minus 20 dB. This is guaranteed, because if you don't have this, then it's not even a type 1 system. So this will always be there. You either extend this line all the way to hit 0 dB line. So this is actually 0 dB. And when you intersect this omega that you see on the graph, that will be KV. Okay, that will be KV. The other way is we find omega equals to 1. You draw this vertical line all the way here and you intersect this line. This point here will be 20 log KV. And from there you read off the graph and solve for KV. Most people like to do the omega 1 method. Most people. Up to you. Okay, so if you're wondering what's KV, it's the measure of how well the system is able to track input. Remember? We talked about this, I think, top here and going through this. So if you want the system to be good, you want the KV to be small. So you can track the system. But you can see from here, just from the Bode diagram, you can recover it. You don't need to actually know the underlying system. That's the nice thing about the Bode diagram. So unfortunately, for this Bode diagram, you need to have a very good sketch shot. Roughly sketching won't be good. So very accurate measurement means from a computer or MATLAB, you can actually recover this. I think in the homework, there will be an example, which I provide you the high quality, very accurate Bode diagram when you estimate from the graph, the KV. Again, these are all graphical methods. You can see there's no calculation. Maybe there's some way to calculate 20 log. That's simple, but by far it's a graphical method. Okay? So this is for the type 1 system. Not first order system, it's type 1. That means there's one pole at the origin. The last one that we will go through is the type 2, where there are two poles at the origin. Right? And in that case, your initial slope no longer minus 20, it's actually minus 40 dB per decade. Okay, so all type 2 systems will have an initial slope of minus 40 dB per decade. can sketch this, then you know. To find the Ka, which is the static acceleration error constant, again, there are two methods. You can extrapolate this minus 40 line and intersect omega A. In that case, this omega A is actually the square root of Ka. So you will need to square this omega A to get Ka. So not quite the same, similar, but not quite the same. The other way is you find omega 1, find the intersection to this initial minus 40 dB value, then this value will be 20 log Ka instead of Ka.
SnC minus 4.
Both methods you can recover Ka. Or the static acceleration error constant. If you've forgotten what this means, you can go to the system type notes and then you refresh the memory of what Ka, Kb, Kp means. So far so good? Everybody okay with this? And so, in this class, you only know 3 types of type 0, type 1, type 2. Technically, there's type 3, type 4, but in this class, we only limit to 0, 1, 2. Okay. So no matter which systems that you encounter, you can always first identify from the Boyd diagram what's the system type, just by the low frequency part. So from there, you can recover the unknown Ka, Kb, or Kp, depending on the system type. It's not like for every system you calculate Kb, 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 no, it's depending on the system type. Type 2, you do Ka, type 1, you do Kb, type 0, you do Kp. Okay? And then to recover each of the values, Ka, Kb, Kb, is a little different for each of the 3 methods. This one requires you to intersect with the 0 dB, and then it's going to square the value. For Ka, Kv, you don't need to square, you just find this value. And then, unfortunately, for type 0, there's no intersection with 0 dB, you just have to find this value here. Okay. So Kv, Ka, 2 methods. Kp, only 1 method.
Yeah, but I don't think you...
Yeah, so if you ignore this title, right, if you're just given this diagram, you should immediately tell that this is a type 0 system because low frequency, nothing, it's flat. And from here, next one, you can see from here minus 20, that means this is type 1. No questions, don't need to do any calculations from just by identifying the next part is minus 40. So only 3, you only have 3 possibilities. Flat horizontal line, slope of minus 20, or slope of minus 40. So almost all the Boyd diagrams that you know, okay, SketchUp will either have these 3 possibilities. Okay, anybody got any other questions? So far for inferring the system type and the static error constant from the Boyd diagram. So again, so look forward to the homework posted tomorrow. Maybe today I'll post it. So the last thing for today is I want to talk about that the Boyd diagram can also help you infer stability. How amazing, this Boyd diagram can do so many things. It's like a jack of all tricks. Okay? So what the Boyd diagram is also very good and very well known for is to determine how stable your system is if you put it into a feedback loop. Okay, so remember we have this transfer function here, this system here, right? And then from this transfer function you can graph out the Boyd diagram. What I want you to imagine now is if this system here, I put it into a unity feedback. So unity feedback is something like this. R and C, right? So this is RS input, CS. Okay. So what I'm going to show you today, or the last thing for today, is that the Boyd diagram of GS can be used to infer the stability if you were to put the system into unity feedback. Okay, I'll say that again. The Boyd diagram of GS can be used to infer stability of the system under unity feedback. Okay, and here I need to introduce two terms for you. One is called the gain margin, and the other is called the phase margin. Both are equally important, and both of them must be positive for the system to be stable. Okay, so there is going to be positive gain margin, negative gain margin, positive phase margin, and negative gain margin. Okay, so let me show you. So for a system to be stable, right, for this system here to be stable, we need to ensure that the gain margin and phase margin is always positive. Okay, so for stability of a closed system, you want to make sure that the closed loops are to the left.
Unity feedback is the feedback loop is one.
That's one way to ensure. The other way is if you are given the Boy diagram, you just make sure that the Boy diagram, the phase margin and gain margin is always positive. How do you infer the phase margin and gain margin for the Boy plot? This is what I will show you for the last thing for today. So this thing is better that you understand graphically than you understand mathematically. So it's actually one of the few things which I say, listen to what I'm saying rather than the equations for now. Okay? So there are two things here, phase margin and the gain margin. So let's do the first one first, which is the gain margin. Gain margin, right? Let's do the gain margin first. So for when you want to analyze the gain margin of a Boy diagram of a system, you look at the phase first. So this is counterintuitive. If you're looking for gain margin, there are two things, because gain margin and phase margin sort of correspond to the gain plot and the phase plot. So you want to find the gain margin, you don't go to the gain plot first. You actually go to the other plot first, phase. So for the gain margin here, we will go to the phase plot here. So these are two plots here of two different systems. The reason why there are two, I'll show you why I need two here. So this is the magnitude plot, this is the phase plot, the black line is the actual graph. So let's try to see how to determine whether the system has a positive or negative gain margin. So gain margin is you look at the phase. Let's look at the phase plot here. And we look at where the phase plot intersects minus 180 degrees. Okay? Simple thing. Look where the graph intersects 180. Then we look, it's right here. My aiming not very good. Okay? So minus 80 intersects the graph at this point. This point is called the phase crossover frequency, where it crosses over the minus 80. Once you find this value, omega p, you go up to the gain plot. Then you go up. And then from here, we determine whether the graph, there are only three possibilities. The graph is, this plot here is on 0 dB. That's one possibility. The other possibility is actually the graph is less than 0 dB, which is shown here. The other possibility is on the right hand side is where the graph is above 0 dB. You see there are three possibilities only. So you look here, look for minus 80 degrees, intersect the line, then at this frequency we go up. And from here there are only three possibilities. You are on the exact line, 0 dB. That is actually 0 gain margin. And from here, we call this positive. If the graph is below 0 dB line, this is positive gain margin. If you look at the example on the right here, if you look here, minus 80, go here, go up here, this is where the graph is above 0 dB. That is negative gain margin. Yeah, verbal explanation is better than the mathematical. So if you want to summarize that in mathematics, it is actually this thing here. Okay, it finds the frequency when it's minus 180, and then determines whether it is below or above the 0 dB line. Okay, so let me go through the phase margin, then I come back to the gain margin again. So this now was gain margin. So if you want to know the phase margin, you don't go for the phase plot, you go for the gain plot first. So let's look at the gain plot here. So we've looked at where the diagram will intersect the 0 dB line. So the lines that are important is 0 dB and minus 180 degrees. So 0 dB is right here. So intersect this line here, we go down. Again here, once you go down, there are only three possibilities. The graph is on minus 180, or above minus 180, or more than minus 180. So in this example here, if you go down, the graph is actually above or less than minus 80. This is called positive phase margin. The other possibility is if you go from here, 0, go down here, you'll find that the graph is below minus 180. This is negative gain margin. So I think that the way to have you think about it is you draw these two lines, right? As long as the margin is in between these two lines, it is positive. You think of the two lines here, right? As long as your margin is between here and here, it is positive. I will explain again one more time for the gain margin. So gain margin is this one here. So whenever you are interested in the gain margin, you start off with the phase. So phase plot, you look for where it intersects minus 180. So from here it intersects minus 80. Then from here you go up and find the relevant same frequency and see whether the magnitude plot is either above, on, or below the 0 dB line. If your plot is below the 0 dB line, this is called positive gain margin. And the amount is a quantity, it's not just positive, negative, you can put a number. The amount is in decibels, you can read off. So it's 3 dB, 4 dB, 5 dB of gain margin. So there are two possibilities, you can get positive gain margin or negative gain margin. Yes?
Why is it called negative? Is it because it's like inverse, so when you log in?
So actually the reason why it's called negative, right, is so that the system will become unstable. When you have negative gain margin and or negative phase margin, the system will be unstable. Maybe I'll explain that later once we see the thing. For you, you want to make sure that the system has positive gain margin or positive phase margin. You'll come back to that later. Good question. I'm going to go to that now. Okay, the question is multiple intersects or what it doesn't intersect. Later, we will go through that. Any other questions? I just want to make sure that you can, for any system, try to determine what is the gain margin and phase margin. That's more important right now. It's actually a visual way. Okay? So I go through one more time the phase margin. Right, phase margin. Phase margin is you look at the gain plot for 0 dB and see where the line intersects the 0 dB line, then you go down. And then from here you determine whether the actual graph in the phase plot is above, below, or on minus 180 degrees. If the graph is like this here, this is positive gain margin. If not, this is you will get negative gain margin, or of course 0 gain margin is exactly. So maybe we can go through an example. Here I have a nice example here. So this is a Bode diagram of this function, k over s plus 2 divided by s squared plus 2s plus 3. Okay? And then we need to specify k when we plot a Bode diagram. So here I put k equals to 1. So this is the Bode diagram of s plus 2 divided by s squared plus 2s plus 3. So let's do some recap of what we did earlier. If you look at the low frequency, you see it's flat. So this is a type 0 system, do you agree? And then if you want to find Kp, you can read off this minus 4. So 20 log Kp is equal to minus 4. Solve for Kp. Yes. So anyway, this is not the point, but here I want to talk about the phase and gain margin. So from here, can you determine using the procedure that I just taught you? Determine what's the phase margin and gain margin of this stuff. Yeah, so let's try. So the first thing is we need to do is if you want to find the gain margin, is we need to find minus 80. But the graph doesn't even touches 180. Never mind. Then you say, never mind. Maybe I'm unlucky. Let's look at the phase margin. So phase margin is I need to find intersection 0 dB. Oh no. So how? So the answer is not no phase margin and no gain margin. You have a phase margin and gain margin. It's just as infinite. You have an infinite gain margin and infinite phase margin. So in your words, do you think infinite is good? Huh? But remember, I told you need to have positive gain margin, positive phase margin. Isn't infinite the best kind of positive? So this system, right, no matter what you do, is always stable. Do you agree with this system? You don't believe it? You find the constant poles of this system, it's always stable. For stability, we need both the phase and gain margin to be positive. So this system, just by looking at the Boolean plot, it's very stable. If you don't believe, you find the closed loop poles of the system and then you solve for all left out. When k equals 1 up, if you change k, that would be slightly different. So let's wait for the next example. So this is a simple example to get you going. Where the phase margin, the gain margin, it's not like 0. Doesn't mean 0. Because 0 has a different connotation altogether. 0 means the system is marginally stable. So it's not like you cannot calculate it. It's just that the gain margin and phase margin is infinite. Your margin is more than what you can measure. So the system is stable. So now let's try something. Let's try something here. So this is the system here. K over s plus 2, s plus 1, s plus 2. Right, and then we set k to 1, and then we sketch the Boolean diagram. Then you get this thing here, and I help you and zoom in for you this part. There's a reason why I zoom in now. It's for you to come in gain and gain margin. I'd like you to take maybe a few minutes to calculate the phase and then the gain margin for this system. Give you a hint, it's not 0, it's not infinite. It's some number, so let you try. Very important. You all can discuss with your friend, but I'd like you all to try and determine the phase margin and gain margin of the system. And I give you the phase plot, the Boolean plot. So this system, you can realize just by looking at the Boolean diagram, at low frequency, this is minus 20 dB per decade. You agree? Next hand side, see this system is type 1. Low frequency, this is minus 20 dB per decade.
Is it positive gain margin?
Maybe I ask another question for looking. Is this a minimum phase system? Is this a minimum phase system? Yes, all the poles and zeros are on the left of plane. So that means this system, if I will give you this diagram here, if I gave you this diagram here, and I told you it was minimum phase, you could have recovered this system. Food for thought. Food for thought, don't to distract you, I want to know the gain margin, phase margin. Okay, I help you. What you want to read? I read for you. So let's maybe we're going to do gain margin first or phase margin first. Okay, do gain margin. Gain margin means we start with the phase. We start with the phase. So we need to find where it intersects 180. So around here, it's about here, or around here. So this 10, right? This 11. So this is what? If this was 10, so this is not 10, this is 1. 10 to the power of 0 is 1. This is 2, right? In between is what? 1.5. So the crossover frequency is 1.5. So from here, you read off, you go up here, and see here, and see whether the line is above, on, or below the 0 dB line. Can you tell me, is it above? Below? Okay, good. When you say below, does it mean that this is a positive gain margin or negative gain margin? Positive, right? So so you measure right now, you do it here. From here, you go up here. This is about 15, and that means the gain margin is about 15 dB. Yeah, so the value is minus 15, but the margin is positive. That's why I need to tell you the gain margin here is 15 dB. Positive, maybe to be more specific, the phase margin is positive 15 dB. Estimate, life is about estimation. Okay, so that is the gain margin. But that's not important, that's not enough. I need to know the phase margin as well. Phase margin is you look for the 0 dB. So from here, you find the intersection and you go down. So I have another plot here that's a little better. 0 dB here, then we go down. Let's see whether this line is above, on, or below minus 180. So is it above, on, or below minus 180 degrees? Above. So that means the phase margin is
you go to 180 here.
It's positive or negative. That's what I know. Positive, right?
Yeah.
Then we worry about what's the value. So now we know it's positive.
No, this one goes
So
down.
we go back here.
We were doing
So
gain
from
margin.
here, we go down.
This one goes down.
About here. Anybody can tell me what's this?
So your
Roughly?
curve is for gain margin or what?
Yeah, why is it?
120?
Wait,
120?
isn't this negative K margin?
about 120 degrees, maybe around that.
The same. Is it the same? Oh, that's
So the phase margin is about 60 degrees. Positive 60 degrees, not negative, but positive 60 degrees. Okay. Most important, I want you to be able to estimate. And from there, determine whether it's positive or negative.
Oh, below, if below 0 it's positive.
Yeah. Then,
Yeah, so if you do that, roughly about 60 up. You see that? So this is the phase margin. This is the gain margin. Okay. So now that you can actually appreciate and identify the gain margin and phase margin, the gain margin, GM, right, is actually another thing that you can use to infer what it means. So the gain margin actually tells you how much your system has in reserve before the system is unstable. Hence the word gain margin. The margin is how much like leeway you have before the system becomes unstable. So remember, this system is actually a closed loop system with this K. Your Bori plot is when K equals to 1. Actually, the gain margin here is also telling you that how much value this K can change before this system becomes unstable. So if you recall, do you remember your Bori diagram of K is just a constant value? So if you think about it, if this graph magnitude right is shifted up by exactly 15.6 dB,
it's down by 15.
then you have 0 gain margin. If you agree, you just shift the graph up by 15.6 dB. You just shift it up. The system will be 0 gain margin, and then your system is actually marginally stable. So if you convert that dB into non-dB value, that's actually 6. That means if you this K, if you change it to by more than 6, means you add in this Bori diagram of 6 inside it. You will push this line up, then you will have no more gain margin.
So then 53.4 is from negative 180
Yes.
minus whatever.
So the requirement for stability is both of them must be positive. If the gain margin becomes negative, it doesn't matter what the phase is will still be unstable. You need both of them to be positive. Yeah, so gain margin will tell you the K value here, how much room you have to take. So ideally, your system, you want to have a high gain margin as possible, so that you have more room to play. So if you find that your system has a very small gain margin, that means you're actually operating very close to this stability coverage. Yeah. So from here, imagine if your system, right now this is the Bori diagram and K equals 1. If you want, you can replot this Bori diagram and K equals 6. And what happens is this graph here will shift up by 15.6 dB. And then if you were to measure the gain margin, it will be exactly 0. Yes.
Wait, you say when K equals to 6.
No need, or you just need to check gain margin. Because gain margin is normally the first.
I mean,
You say
sorry?
when K value
Normally,
equals to
usually,
6,
Ah, why not?
then the whole graph will shift up.
Oh, I
but the
never listened
requirement
to
is both of them must be positive to be stable.
I figuring out that.
Yeah, I know what the K value is.
Because, no, K when K becomes more than 6.03. Actually, because
So I think the 6.03 is when, I guess it reaches 0. If that's a negative 6.03 ma. Just want to plus 6.3 to 6.3.
you can see already it's more like not adding, it's
You
multiplying.
know, you shift the whole thing up.
Something like
Yeah. But
Six,
how
right?
does K
And the
influence?
K,
How
this
does
is
K
so
influence
Because when we do the word again, you sketch them by
他不讲 shift
multiplying the
when K equals to 1?
Sorry?
When K equals to 1?
So right now,
K equals to
K
6.03.
is 1.
Or equals to
So
10.
it's
Yeah.
easier for you to determine if you were to change K to by multiply by 6 or change it to 6, you will have the same effect.
That's what the margin for, I guess.
The shift.
So ideally, your gain margin needs to be positive and a significant amount of number. This is actually okay. It's a little low, but you want something higher. So the gain margin, phase margin for any system can be used to infer how good the system is with regard to robustness, like how close is it to be unstable or stable. This is something that you normally cannot infer based on looking at the spec. But the phase margin or the Bori diagram can tell you. Yes, so if the gain margin is negative, and the phase margin is positive, it's still unstable. We need both of them to be positive to be stable. Until, that means you are marginally stable. It means you are on the verge of instability. Nobody operates there. It's not measurable. It won't be measurable. So when K, imagine, when K is 6.03, the Boyd diagram will shift up by this 15.6 dB. So you get 0. So remember, K only shifts in magnitude, right? Phase what change. Do you agree? Right? That's the key part of the K. You only shift magnitude, your phase is always 0. Nothing to do with that. Stability is whether the value will go to infinity or not. Yes. Yeah, so if your system has 0 phase margin, you can do that. This is the value does not grow, the value does not die off. Keeps oscillating. The system needs to be undamped going to this response. Because if you damp, then you die. But once the system is damped out, you will be stable. It's related. Yeah. Yes. It will be if you were given the Boyd again with K equals 2, then the gain margin will be slightly different. It won't be this. Is multiplication with a change in the dB. Because we have to read the dB. It's 20 log the value. So 20 log 2. Cannot calculate that. So you will always be, in order for the Boyd diagram to be shown to you, the K value will be low. It will be low. Of course, 1 is the easiest, right? 1 is just the easiest. It can be like 10 also quite easy. But anyway, the whole point is if you from here find the gain margin, find the gain margin, phase margin, and the gain margin will tell you how much leeway the K can change before the system becomes stable. And then very important is given any system, whether you know whether the system is positive or negative gain margin. That's very important. So if let's say there's no calculation of this, just remember the 2 lines.